Okay, so you've just taken the survey of when to do your research presentation. You have a homework assignment due on Friday. We're going to go over another example today in class that will help you to solve that assignment. We've just done quiz 5. I wanted to make good on a promise I think I made earlier in the semester that I would share with you some library resources. I'm glad somebody mentioned it to me that I hadn't done that yet. I think that the best place you can go to get reliable, peer-reviewed, like robust, scientifically accurate and meaningful articles is just go to library website. So library, and then here under article databases, you choose that, and then popular databases. The top popular database here, alphabetically, is Academic Search Complete, which sounds promising, and it is. If you click on Academic Search Complete, you have to do this from either on campus or I think you may need to log in to be able to have access to this database because it's a subscription that Marshall pays to have access to. So you'll notice here it's branded with Marshall's logo because it's detected me on campus. But now if you put in a topic like ozone disinfection of water and search, then you can identify the range of dates. And in your project, I want you to tell me like what's the most recent meaningful research, like where are things headed? And so maybe to be the most informative, I'd want to know just what research has been done in the last 10 years. And so you can filter the dates from the last 10 years. And you can see the number of hits that we've got here, 127 from academic journals. And if I want to exclude like book reviews and magazines and trade publications, just select only the academic journals. Then some of these Marshall will have the full text too. Others you may only have access to the abstract. But you know, here we've got quite a lot of options available, and just reading through the titles even, you can maybe get a sense for what people are studying in a given topic. So again, I just wanted to point out that I think maybe the most robust and fast way to get access to high quality peer-reviewed journal papers isn't necessarily Google searching. I think it's through this paid database that you've got access to through the library, Academic Search Complete. Okay, so let's continue talking about noise pollution. And we've got a kind of an interesting in-class exercise that I brought rulers for. You don't normally need to use rulers, but we've talked about some of the effects that excessive noise can have on people, how it's associated with developmental delays, reduced cognitive performance, it interferes with sleep. And once you interfere with sleep, that reduces every other health and mental wellness outcome imaginable. When you interrupt people's regular sleep, it's going to increase their blood pressure. It's going to worsen their blood markers when it comes to liver function, kidney function, cholesterol. Everything gets worse. Hormone status, everything gets worse from interrupted sleep. And so, you know, noise has a direct impact on that. And so there are a lot of different figures that assess the effect of noise, and this figure just focuses mainly on the difficulty of communication, where you've got a certain amount of background noise on the vertical axis here, and how close you are to another person, and whether communication is possible. So this range above the top curve of communication impossible, if you're 3 meters away from somebody in an environment where the background noise is 100 decibels, then communication is impossible. Even if I was shouting at you with my professor's voice, if we were in, let's say, the blower room at the Huntington wastewater treatment plant, we wouldn't be able to hear anything. So that's one way to evaluate the effect of noise. Effective noise has been studied by the Federal Highway Administration for housing standards and trying to assess either on an average basis or looking at a more obscure measurement of noise, which is this L10. So there's two different columns here. One, the LEQ, is just kind of like a time-weighted average of noise, whereas the L10 is an amount of noise that is exceeded 10% of the time. So rather than just averaging, you're kind of looking at like how bad does it actually get during the worst of times, maybe during rush hour traffic, when roadway noise would be the worst. And so this kind of is describing the amount of noise that is appropriate for different types of uses. And so buildings like hospitals, churches, libraries, where we kind of understand and recognize that a low amount of noise is required for those sorts of activities, then you'd want in the interior spaces a noise level of 52 on a daily average and 55 on an L10 basis. So that would mean with the effect of soundproofing combined with the noise that's on the outside, you need to get under that standard. The rest of these are just based on kind of an outside noise rather than inside the building. So this is saying that hospitals, public areas, schools, and so on, if you're talking about how much noise is appropriate for the outside, then it would be 67 decibels on an hourly average, like if you average it across the day, or the L10 70. So what they're suggesting is that, between the construction materials and the enhanced windows and so on, you should be counting on, at most, the building materials bringing down the sound levels by 15 decibels. There are other types of developments that we're maybe less strict with, so like an outdoor park. We don't want them to be, actually, no, the outdoor park has a lower standard. So quiet is of extraordinary significance. So yeah, special types of parks or protected areas would be in this land category A. So we don't always know in advance how noisy things are going to be, but there are ways for us to estimate and kind of project into the future what it may be. And the example that we're working on today is related to Federal Highway Administration and like automobile-based noise. The other big source of noise generation that has experienced a lot of study is aircraft noise. And so whereas this first one was related to the combination between housing and roads, the FAA, the Federal Aviation Administration, has also looked at the effect that aircraft have on what's suitable for different types of environments. And they have a weighted average that takes into account the extra significance of noise during nighttime hours. And so this L sub dn is just a way of calculating an annual average and then assigning penalty points, so to speak, to noise at night. And there are certain airports in the world where they just don't accept flights at all between midnight and 8 a.m. I remember, for example, I was flying into Switzerland, which has some really strict regulations on a lot of different fronts, one of which is aircraft. And because of a favorable jet stream, we arrived earlier than expected, but we couldn't land. We just kind of had to circle the outskirts of Zurich because we weren't allowed to land before, I think it was 8 a.m., because they have really strict noise requirements there. The same isn't true everywhere, but because of the effect that noise has on sleep quality, it's an important consideration. There are things we can do to reduce the effect of noise, and where I notice it the most is during a power outage. I live in kind of a rural area where probably 10 times a year the power will go out for several hours at a time, because it seems like anytime the wind blows hard or if it's a rainy day, inevitably a tree is going to fall over and take down the power lines. And so then everybody starts up their generators. And generators are really loud. They're noisy. Some people have automated generators that are in like a nice case that kind of muffles the noise a little bit. But a lot of people, myself included, don't have an automatic generator. You have to kind of wheel it out or set it up on your driveway, and then you can kind of just hear when the power is out because of all the machine noise. So remember that noise is generated from vibrations and collisions of surfaces on each other, compressing and contracting the air, and then that shock wave of energy propagating through the gases of our atmosphere. So if those waves are radiating outward from a noise source, some of the ways that you can reduce the intensity of the noise is, first of all, to isolate the noise source. You can see here it's showing spring mounts. So if it's mounted on springs, that's kind of absorbing some of those vibrations rather than transmitting them through the ground. That can be one way to isolate the noise, especially low frequency noise. And then the other part of it is just setting up barriers to intercept the noise waves as they emanate from the source. The problem being that a lot of times the things that are generating noise are also generating heat. And so we can't put them in like a fully enclosed box, because then, whether it's somebody's heat pump at their house needs a lot of airflow without us trapping warm air around the heat exchanger. Otherwise, it's not going to get the house cool during the summertime, and it would, if it's a heat pump and it's warming up the house during the winter, you need to have plenty of airflow as well. So it's not practical to have complete enclosure, but here what this is illustrating is a series of baffles, so that you could, in theory, have the air coming in, and maybe you're using a fan to induce the ventilation through the enclosure box. But the sound waves would have to take such an indirect route to get out of the box that they be largely absorbed and dissipated by the box and the acoustic lining that's on the inside of the box. So I've thought about building something like this for my little portable generator, and maybe one of these days I'll get around to it now that I've got a diagram here. The key idea is to attenuate noise. You isolate the vibrations of the noise source. And the same thing is true with highway noise. You've probably seen noise walls along interstate highways. There's one that I've seen a couple of times recently up in Columbus, where it's just a gigantic concrete wall, and I assume that there's houses on the other side of it, and there isn't any noise that's going to get through that concrete wall. So one of the homework assignment problems you've got asks you to calculate the equivalent continuous energy level, LEQ. And this calculation is a way to average over the course of a time period when the noise levels are changing and express it as an equivalent amount of energy over the duration. And so here you can see the averaging formula. What you do is you take the individual sound levels, divide them by 10, and 10 to the power of that number multiplied by the increment of time, and then dividing by the sum of the times. And so just to get a feel for how all of this works, let's say that we had 10 minutes of 90 decibels followed by 30 minutes of 70 decibels. And so what would be the equivalent continuous energy level over the 40-minute time period? So what we would do here is we'd say we have the 10-minute time period where the noise level is 70 decibels. And so 10 to the power of 70 divided by 10. And then we're going to add that to, multiply it by the time, 10 minutes. Okay, and then add that to 10 to the, that was 90. 10 minutes is 90. Plus 70 decibels for 30 minutes. So 10 to the 70 divided by 10 times 30 minutes. And we've added them together. There's only two of them. and then divide by the total amount of time. So 40 minutes. And then we're going to take the log base 10 of that and then multiply it by 10. So if you've got your calculator, hopefully you do, we just had a quiz. Let's calculate what is the equivalent continuous energy level here. So 10 to the 9th power. 10 to the 7th. .1 decibels. It's kind of like the time-weighted average. The equivalent continuous energy level. So on the homework, I think I do the same thing where I tell you, certain times of day, from this time to this time, from midnight till 6, it's quiet, then from 6 to noon, it's loud, and so on. So you're just you're weighting the intensity of the noise with the duration to find out a time-weighted average. Anybody have any questions about that calculation? Okay. So, how do we predict it in advance? I mean, it's easy enough to measure once it's there. But for planning purposes, we can't wait until the noise is being generated. We need to build a home and kind of assess what will be the noise level that home is encountering even before the highway is built. So there is kind of an odd figure that we're going to use. It's called a nomograph. And these used to be a lot more common than they are now, nomographs. Now we generally have software programs or equations that can achieve most of what previously was done with nomographs. But for highway noise prediction, it can still be useful to understand this nomograph. So these instructions that are here are about how we can calculate this L10 parameter. L10 is the noise level that's exceeded 10% of the time. So it's not the average amount of noise, but you can think of it as almost as loud as it gets. Only 10% of the time is louder than the L10 level. So if you are designing for the L10 level, then 90% of the time it'll be quiet enough. All right, so let me hand out the in-class exercise paper. What we're going to be doing is trying to understand what's happening for a hypothetical weighing station. You've probably seen these on the highway before. There are places where trucks have to pull in and get weighed, and the rest of the traffic can continue on, doesn't have to pull in. I think there's one on I-64, right? What stop is that by? Is it by like Hurricane? In the vicinity of Hurricane, I think. So the trucks are going slowly, and the cars and medium-sized vehicles keep going past quickly. So the trucks are close, they're bigger, they're louder, and part of what makes them louder is the fact that they're higher off the ground. In fact, that's a big part of it, is that the trucks are elevated, so their engine noise carries more. It carries further than a vehicle does. Also, trucks have more wheels, and wheels are a big source of the noise. So all of that is taken into account in this very strange figure. Oh, you also need these rulers. So we're going to walk through this together. By the way, don't steal these rulers. These are state property rulers. Do any of you carry those triangular rulers like in your backpack? Have you seen those before? Some of you do? You got one? All right. Well, because I apparently didn't bring enough rulers, so you're going to have to share. If you've got one of your own, yes. Although these clear ones can be helpful, if you don't need it, I'll pass it along. Some of you are prepared. I love it. I think we didn't have enough back here. All right. Well, I'll let you continue to pass them around. So what we're going to do is start with the automobiles. Let's just assess all the stuff that's happening here. So we're building a weigh station, and we want to predict in advance how noisy it's going to be at the building that the workers drink coffee in and watch traffic go by. So that building is going to be 15 meters away from where the trucks drive and 70 meters away from where cars and automobiles are. So the cars and automobiles are whizzing past at higher speeds. The heavy trucks are moving slowly, and then the terrain is level with no shielding. If there was like a berm or if a big elevation difference, then we'd have to make some further adjustments. But here, terrain is level with no shielding, and that's the same case as you'll face on the homework assignment. Okay, so the way this works is, first of all, we'll do automobiles. We know their speed is 110 kilometers per hour. So on the figure that I've just given you, and by the way, you have to be precise. Like even if you're off by a couple of pencil widths, then that's going to have dramatic consequences on the noise levels. And so really pay attention to trying to draw your start with the actual pivot point. So we're going to draw a line from the pivot point through the speed of the automobile, 110, and stop at line A. So just a single line from the pivot point through 110, the lower one for automobiles and trucks, and stop at line A. And you can just, next to that point where the line comes into line A, just write A1, very small, not on the intersection point, but just near it. So that's automobiles. Okay, next, we're going to draw a line from the A1 intersection point through the volume of 3,000 vehicles per hour. So take your ruler and find the A1 point and 3,000 vehicles per hour and just draw a line connecting the two. So if I'm going back through these instructions, we're now doing the line 2. And the point of intersection that we're interested in is where it crosses B. So the line was from A to 3,000 vehicles per hour. And then make a special note where it crossed B and label that as B1. Now there's one more step, and that is draw a line from B1 to the distance of 70 meters. So D sub C is 70 meters. Let me see if I can draw lines on this thing. So first of all, we had this line through 110, and then from 110, or from point A over to 3,000 vehicles per hour, and then from B, this is point B, to 70 meters. Okay, so the noise from automobiles is 67.5 decibels. See where it crosses this dBA? It looks like it's halfway between 65 and 70. So I'm going to say auto L10 equals 67.5 dBA. And by the way, dB is decibels. A means like A weighted. It's just there's a couple of different ways of measuring decibels, and there's an A weighting system. I don't know all the technical details, but that's how this is generating it on the A weighted decibel scale. So does anybody need me to go through that again on how we did automobiles? Okay, medium trucks is similar, except there's a twist. Medium trucks are assumed to be at the same height off the road as automobiles, but because they're heavier, they generate more noise, and the way this system accounts for that is you multiply the traffic volume by 10. So what we know is that we have 200 vehicles per hour. So put in parentheses, times 10 equals 2,000, because you're going to treat it as though there are 2,000 vehicles per hour for medium trucks. Okay, so medium trucks, 90 kilometers per hour. I'm going to remove my previous markers here and go through the same process for the medium trucks. I won't be narrating it, but I'll be doing it up on the screen here. Okay, so I think that the noise level for medium trucks is about L10 of 64.5 decibels. L10 is 64.5 dBA. Anybody else agree with that? Yes? Okay. So we multiplied the volume by a factor of 10. Had a different speed. That gives us the medium trucks. And you can label your turn points as, you know, like A2, B2. Just, you know, like if you're keeping track of what came first was the autos, then we did the medium trucks, and so on. All right, lastly, we've got the heavy trucks, 300 vehicles per hour, and they're going slower because they're going through their automated weighing lanes at a speed of 30 kilometers per hour. So we're going to use that top part of the figure for the heavy trucks, not the bottom part of the figure. So I'll delete all my previous marks here. Let's do the heavy trucks. Oh, by the way, extend line A. I think line A probably won't be long enough, so you can just extend line A a little bit further. What did you get for the heavy trucks? much?
76.
It should be above 80 because what we're doing is we're taking the turn point from B up to 15 meters. Remember that the distance is closer for those heavy trucks. That's the curveball. The heavy trucks are closer than the rest of the traffic was. So, heavy truck. L10 is, I'm calling that 85, 87 dBA. That's quite a bit louder than everything else, even though there's more autos and more medium trucks, and they're going much, much faster, but they're further away. And remember that the energy is radiating in 3 dimensions, and so distance, as distance increases, the sphere that the energy is dissipated over, the area that the energy is applied, is increasing non-linearly. It's increasing with, I guess it would be distance cubed. No, that'd be volume. Distance squared. So now we want to combine it. So what is the combined effect of this noise, the LW? You know, combine the 3 different L10s together using this same kind of weighting that we've done before. So the combined L10 is 10 times log of 10 to the 6.75 plus 10 to the 6.45 plus 10 to the 8.7. So the autos and the medium trucks have almost no effect. The combined noise level is going to be just above 87 decibels because the medium trucks and autos don't really add that much more. Darn it, I've done it again. It's 151. I kept you over. That's it for today. I'll get those quizzes scored. I'll look at your survey preferences and then let you know when you're going to present the, when you're going to do your presentation. Oh, that's not the right one. So check Blackboard for that. I'll let you know when it's posted.